Mhm. Okay. Hello everyone. So today is the sixth problem solving session for the course Introduction to Lasers. So I will just wait for a few minutes for others to join and then I will start. Okay, so today I'm going to discuss about the laser cavity modes, and then I will solve some problems regarding this. So it is the laser. So here we are going to discuss about I'm going to discuss about the different modes that are present in the laser cavity, that is transverse and longitudinal mode. But before that, for longitudinal laser cavity modes, I will first discuss about the Fabry parrot resonator. Okay, so now for longitudinal mode, what I am going to discuss, that is known as Fabry parrot resonator. So basically, the Fabry parrot resonator is an optical cavity made from two parallel reflecting surfaces. Okay, so when mirrors are placed at the end of an amplifying medium, they place a boundary condition on the electromagnetic radiation field or the laser beam. So now when this kind of things happen, there is a certain mode arises inside the cavity. So we expect that similar type of modes can develop also within the laser cavity with similar boundary condition, such that the such that the electric field is zero at the boundary. So now, we'll start with the Fabry parrot resonator. So what is Fabry parrot resonator? So first of all, the convention I am going to use for this particular resonator is that this is one of the mirror. Okay, now so this is the incident electromagnetic wave. So this is the perpendicular, so this angle is theta. Then this is the reflected wave, that is also has a theta with the perpendicular, and this is the transmitted wave. So now E naught is the amplitude of the electromagnetic wave, Now I will define two coefficients. One is t, another is r. Small t and small r. So small t is the coefficient of transmission, r is the coefficient of reflection. Okay, so now this is the incident beam has a amplitude E naught. So the incident beam has a beam of light of amplitude E naught is incident upon a partially reflecting surface. So this surface is partially reflecting. Sorry, partially reflecting surface. So now the transmitted beam will have amplitude E naught t, and the reflected beam will have a amplitude E naught r. So what is this? Basically, E naught equal to E naught t plus E naught r. So some part of this is also absorbed by this surface, but if there is no absorption, then under that condition it will satisfy this equation. So that means that t plus r equal to 1. Okay, so as we are discussing of modes, so that is a time independent standing waves. Time time independent so you don't need to bother about the time dependence of the electromagnetic wave, so we can neglect the time dependence for now. Neglect time dependence of EM1. Okay, so now we will come to the real fabric resonator, that is this two reflecting surface. So two reflecting surface is there, and the now the condition. Okay, so now the condition for these two reflecting surface is that these two reflecting surface has same coefficient of reflection. So coefficient of reflection equal to r, and coefficient of transmission equal to t. So these two applicable for both the reflecting surfaces. Okay, so now, so these two reflecting surface, or here you can say these two are mirrors, not perfect mirror but partially reflecting mirrors. So these two mirrors have same property. So coefficient of reflection equal to R and coefficient of transmission equal to T. So these two property applicable for both the reflecting surfaces. So now when an electromagnetic wave with a magnitude amplitude E naught will come here, it will suffer two things. One is transmission and another is reflection. So first of all it will transmit, and from this surface it will reflect. So this beam has, if this beam has a uh, amplitude E naught, then this beam will have an amplitude E naught T, and this beam will have amplitude E naught R. So again, so E naught R is already not coming inside the cavity, so we will not bother about this particular beam for now, but E naught T is coming inside the cavity. So now it will again suffer two things from this particular, this is, let's say this is first surface, this is second surface. So from second surface it will transmit again, and also it will reflect. So here the coefficient of reflection and transmission are same, so E naught T will be transmitted with the amplitude E naught T square. So basically it is multiplied with the T, and then the reflected part will be, so E naught T square is going outside the cavity, so we will not consider this for now, and E naught T will, the part of E naught T that will be reflected from the second surface is E naught T R. Okay, this looks like a E naught T R. Now again from this surface there will be a reflection and a transmission. So in my drawing the angles are not same, but it is should be same. So this transmitted part will have E naught T square R, this reflected part will have E naught T R square. Then from this surface it will be E naught T square R square, and the reflected part will be E naught T R cube. Then it will have E naught T square R to the power 3. Then so I will not draw this for infinity, I will just write some terms to draw some beam. So here it will be the beam that is E naught T R cube will have E naught T R to the power 4, then it will be E naught T square R to the power 4, this will be E naught T R to the power 5, this one will be E naught T square R to the power 5. So if you check the uh, amplitudes, you can see at this side and in this side. So in order to have the beam outside the cavity, there are two possibilities. Either this beam will be reflected from the one surface, that is this one, E naught R. Otherwise the beams will be transmitted through two surfaces, so it should have this T square term. So either there is no T square term or there is one T square term. So you can find that here it is the T square term, T square here, or T is also we have the T square term, and then here and then. Okay, so now after that it is just depends on the number of reflections. So if it is coming from this surface, then it is E naught R. If it is coming from another reflection from second surface and then a transmission from the first surface, then it has one which is, I mean, I'll just try different colors to, but so if we are talking about this beam, then it will be E naught R. If I am talking about the second beam, then it is E naught T square R. If I am talking about the third beam, then it is this and this. So it will be E naught T square R cube. And if I am talking about the fourth beam, then it is this, and this. This is E naught T square R to the power 5. Okay. So similarly, if we think about the transmitted beam, then we will add this beam, amplitude of this particular beams. So now we can now sum up all the transmitted amplitude as Et. The small t is for transmitted, E naught T square. So E naught T square is this one. Then E naught T square R square. Naught T square R square e to the power I phi. So now there is an interesting thing. I will just write that this, what is this I e to the power I phi term I am writing. So whenever this beam is so basically from this beam to this beam, there is a extra path length that is covered by the beam, that is, I'll just use a different color here, that is from here to here. Okay, so this path is extra for every this beam. So from here to here, this the beam is traveling this extra path, so we have to consider that difference. In order to calculate that, we will just draw the mirror again, and from simple geometry we will have the result. So this is one beam, this is theta, this is theta, this is A, and this distance is D. So now A equal to D by cos theta, and the path distance, that will be this. So the bold line is the extra path distance, so A and B. So here B equal to A cos 2 theta. because this is 2 theta basically. So now the total additional path is a plus b. D cos theta 1 plus cos 2 theta basically. So it will become a d cos theta 2 cos square theta. So it will become 2d cos theta. Okay, so 2d cos theta. So now I will calculate the term phi. So as we know that e to the power I k z is the phase term that is related to the so basically the phase difference that is introduced in the beam is depending on the path difference, and that is here it is written as z. So the phi equal to kz k into 2d cos theta. So that will be 2kd cos theta. So now if I replace k by lambda, that will be 4 pi by lambda d cos theta. So this is the value of phi. So I'll just write the value of phi again, 4 pi d by lambda cos theta. Phi equal to 4 pi lambda d cos theta. Okay, so now I will just write this equation that I have discontinued writing. I will just write this again. Et equal to E naught t square so E naught t square is this term, then I will write this term and this term and so on. So E naught t square, then E naught t square r square e to the power I phi. So here the phi means this one. So this phi means that the phase difference between E naught t square and E naught t square r square is this, is basically phi. Then I will write this term E naught t square r to the power 4. E naught t square r to the power 4 e to the power 2 I phi plus dot dot. So this is if you closely look at this expression, you can easily observe that this is basically a sum of geometric progress GP series or geometric progression series. So we will just take E naught t square common, write it as 1 plus um, r square e to the power I phi plus r to the power 4 e to the power 2 I phi dot dot dot, and here it is the infinite GP series. So this is a geometric series with a ratio successive terms of r square e to the power I phi. So again this is can be expressed as et equal to e naught t square summation n equal to 0 to infinity r to the power 2 n e to the power I n phi. So this will be 1 by, so now this is the geometric series. So the value of this is n equal to 0 infinity r to the power 2n equal n phi equal to 1 by 1 minus r square e to the power I phi. So I'll just put this value here and we will have et equal to e naught t, sorry, e naught t square 1 minus r square e to the power I phi. Now the transmitted intensity is expressed as it equal to modulus of it square of modulus of it is et. So it will be e naught square t to the power 4 1 minus r square e to the power I phi square. It will be I naught t to the power 4 by 1 minus r square e to the power I phi square, where I naught is the equal to the square of modulus of e naught. So now during transmission we have added the additional path length, but during reflection we can think about r equal to modulus r e to the power I phi r by 2. So here phi r will have either 0 or pi. So phi 0 is from when we are going from a more dense to less dense medium, and phi is for vice versa, not vice versa, opposite case. That is, it is going from less dense medium to more dense medium. So now if we define the reflectivity as r equal to square of modulus of r small r and t equal to square of modulus of t, so then we can write it as it equal to I naught t square, so t square 1 minus r e to the power I capital phi whole square. So this capital phi means this is capital phi equal to phi plus phi r. So this means that the phase change due to additional path and reflection. So basically, if the reflection is from more dense to less dense medium, then this phi r will be 0, and if it is from less dense to more dense medium, then this phi r will be 5. So now the expression in the denominator can be rewritten as 1 minus r e I phi r e to the power I phi multiplied by 1 minus r e to the power minus I phi. So here I have used the formula, that is modulus of a square equal to a multiplied by complex conjugate of a star. So now this, I will just multiply this and we will have 1 minus r e to the power I capital phi minus r e to the power minus I capital phi plus r square. Now from this term we will have 1 minus 2r cos phi plus r square. Then we will write 1 minus 2r plus r square plus 2r minus 2r cos phi. So this will become 1 minus r whole square. As r is less than 1, so we can write 1 minus r, and that will give a positive quantity here. 1 minus r whole square, then 2r, if we take 2r common, then it is 2r 1 minus cos phi 1 minus r whole square 4r sine square phi by 2, then 1 plus 4r 1 minus r whole square sine square phi by 2. Now we'll set a quantity f dash equal to 4r 1 minus r whole square. Then we can write it equal to I naught t square 1 minus r square, sorry, 1 minus r whole square 1 by 1 plus f dash sine square phi by 2. Okay, so 1 by 1 plus this is known as Airy function. Any doubt regarding this calculation?
So can you solve one problem with this?
I'll do that.
Okay.
Okay, so now after that we can write IT by I naught as 1 plus it dash sine square pi by 2. So now the maximum value of IT by I naught will occur when the phi by 2 is n pi, that is we will have sine n pi. So phi max is 2 n pi. So now here we can write this as 4 pi lambda naught d cos theta plus phi r. So this is from the previous equation I have used here. Here now one interesting thing we will find out, that is the FWHM. So to obtain the FWHM we need to equate this to half. So FWHM means full width at half maximum. So 1 by 1 plus f dash sine phi by sine square phi by 2 equal to half. Now one thing we will do, that for large value of r we can write sine square phi by 2 as phi by 2 square. Okay, so then we can write 1 plus f dash phi by 2 whole square equal to half. From here we will have phi dash equal to 2 by root f. FWHM here is 2 phi dash, it is 4 by root f. So we will now define a quantity f. This is known as the fine finish of the cavity, so it will be denoted as delta phi by FWHM. So the delta phi, maximum value of delta phi is 2 pi by the FWHM is 4 root over f dash. Then we will have pi f dash by pi root over f dash by 2. So now the value of f dash is this one, 4r by 1 minus r whole square. So we can write that here, and then we will have pi by 2 root over r minus 1 minus r. That will be simplified to pi root over r 1 minus r.
Hello, sir.
Yes,
Can you explain how the previous equation? Can you just
which one?
this one finesse. So 2 pi by 4 root of f dash.
Hmm.
How is pi root f divided by 2, sir? 2 by 4 will give you 2. And how far the root f comes to numerator?
Oh, okay, okay. Ah,
Ah,
4
yes.
by root over f dash, right?
Yes, yes.
Yeah, actually I write it here, but it is not written in the pad. Sorry about that.
Okay. Okay.
Now it's okay, I think.
Yes, yes, yes.
Yeah, 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 it's working. Yeah. So now if the reflectivity of the two surfaces are different, then this f will be changed to pi r1 r2 1 by 4 1 minus r1 r2 half. So this thing can also be derived with this similar process, but I am just writing the uh, equation straight away. Okay, so now I will just go to some problems. So before that, there is a thing that is the frequency difference of modes. So the frequency difference of modes is, so it, to obtain the frequency difference between modes, we will start from the equation phi max equal to 2n pi equal to 4 pi by lambda naught d cos theta plus phi r. Okay, so if we set theta equal to 0 and phi r equal to 0, so basically theta equal to 0, we I am want to say is that this thing, that this incident beam is like this and this, the angle is very small. Okay, and then the phi r is 0, that is the reflection is from more dense to less dense medium. Okay, so in that case we can put theta equal to 0 and phi r equal to 0, then we will obtain 2n pi equal to 4 pi d by lambda naught. Then the value of n will be 2d by lambda. Okay, so So now lambda n max that can be obtained in the cavity is 2d by n. Okay, so from here the nu or the frequency of that particular mode will be nc by 2 eta d. Eta is the refracting index of the medium. So this is the nu max. Now we will take nu max. So n plus 1th, the new maximum frequency for the n plus 1th mode minus the maximum frequency for the nth mode will be c by 2 eta 2 eta d n plus 1 minus n. This will be c by 2 eta d. So new shape equal to c by 2 eta d. Now let's see some example. So the first example is determine the frequency difference between successive maxima for a Fabry-Perot interferometer in which the mirrors are separated by 0.01 meter. So the difference is 0.01 meter and we have to calculate the new set. Okay, so in order to have that, and here it is mentioned that the mirrors are so we need to find out the delta nu shape, and the mirrors are located in air. So that means that eta will be 1. So now nu shape equal to c by 2 into 0.01. So that will be 3 into 10 to the power 8 by 2 into 0.01. This will be 1.5 into 10 to the power 10 hertz. Now I will then again do another example, that is here compute the FWHN frequency line width for a FP cavity. So the FP cavity means Fabry-Perot cavity with two identical mirrors. Now the distance between the mirrors is 1 centimeter. I'll just write the values. I am not going to write the whole problem because it's not necessary. And the medium is air. So now there are different reflectivities are given. One, R equal to 99.99%, 2, R equal to 95%, 3, R equal to 70%. Okay, so now there is a next part of the problem, that is, so in the first problem we need to calculate the FWHM frequency line width. And the second problem, determine the cavity Q if the output is gallium arsenide diode laser output of a gallium arsenide diode laser with lambda not equal to 800 nanometer is transmitted through this interferometer. Okay, so now let's just write down all the values we have in the problem. D equal to 0.01 meter, lambda equal to 800 nanometer. Then there are three values of R, 99.99% for the first problem, 95%, 70%. Then the refractive index eta equal to 1 as it is here. Now delta nu equal to C by D, 2 eta D, so it will be 3 into 8 by 2 into 1 into 0.01, it will be 1.5 into 10 to the power 10 hertz. Then again the nu naught will be C by lambda, so 3 into 10 to the power 8 by 800 into 10 to the power minus 9, it will be 3.75 into 10 to the power 14 hertz. Now delta nu FWHM is delta nu by F, where F is pi root R by 1 minus R. Okay, so this formula is going to be used, and then there is another formula, that is nu naught by mm, nu naught by delta nu FWHM. Okay, so this formula and this formula is going to use to find out the answer. So for part A, R equal to 0.9999, F is 3.141 into 10 to the power 4. So this is calculated from this particular formula, where we put the value R equal to 0.99999, and we obtain the value of F. Then we will delta nu FWHM equal to delta nu by F. So delta nu was 1.5 into 10 to the power 10 hertz divided by F, 3.141 into 10 to the power 4 hertz. So then F don't have any unit, so it will be 4.78 into 10 to the power 5 hertz. Now the Q is known as also the quality factor of the cavity, which will be calculated by using the formula nu naught delta nu FWHM equal to 3.75 uh, 3.75 into 10 to the 14 hertz by delta nu FWHM is 4.78 into 10 to the power 5 hertz, so it will be 7.85 into 10 to the power 8 hertz. Now this procedure will be followed for the next two cases. I will write down. So for R equal to 95% or 0.95.
Sir, qualitative in terms of picture,
Sorry.
is it correct? Q unit is Hz. 7.8 and 10 to the power of 8 hertz is it correct?
Sorry, I cannot
7.
hear your question properly. Too much noise there.
Okay, sir.
Can
Continue.
you write down if it's possible?
Okay, okay. Sir, I lost later, sir. You please continue this.
Okay. Okay. So R equal to for 0.95. So the F will be pi root over 0.95 by 1 minus 0.95. It will be 61.2 del delta mu F W H n equal to 1.5 into 10 to the power 10 by 61.2, that will be 2.45 into 10 to the power 8 hertz. Then the quality factor 3.75 into 10 to the power 14 2 by 2.45 into 10 to the power 8 will give 1.53 into 10 to the power 6. Now C R equal to 0.70, then F equal to pi root over pi multiplied by root over 0.70, 1 minus 0.70, that is 8.76 delta nu equal to, sorry, delta nu FWHM equal to 1.5 into 10 to the power 10 by 8.76, that is 1.71 into 10 to the power 9 hertz. Then Q equal to 3.75 into 10 to the power 14 by 1.71 into 10 to the power 9. It will be 2.19 into 10 to the power 5. So now we have the value of F and Q for different reflectivity. So now I can write down a table. So first R, then F, then Q. So R is 99%, this one is 95%, then it is 70%. Now if I write down the value of F, what is it? 3.141 into 10 to the power 4. So 3.141 into 10 to the power 4, then 95%, 95%, 61.2, then C is 8.76. Then if I write down the value of Q, 7.85 into 10 to the power 8. 7.85 into 10 to the power 8. Then 1.53 into 10 to the power 6. 1.53 into 10 to the power 6. Then 2.19 into 10 to the power 5. Okay, so here you can see that with decreasing reflectivity, or there is a loss due to the transmission, the f and q value is decreasing. So basically f and q value are kind of quality of that cavity. So the better the value of the f and q, or the value of f and q is higher for a certain cavity, the sharpness of the beam from that cavity will be better. So these are measure of the sharpness of the frequency transmission under consideration. So these two things are basically unitless quantity, which actually gives us the sharpness of that cavity. Okay, so this is the thing, like the better the value of f and q, the better the uh, cavity is for using inside a laser. Now another thing that we can calculate, that is mode number. So this mode number is calculated mu equal to n c 2 eta d, then if there is a uh, distance between the gain medium and the gain medium is situated inside the cavity. So basically it is situated between the two, located between two mirror. So if there is a distance between the gain medium and the mirror, then this formula will be modified to n c by 2 1 by eta c d minus l plus eta l l. So l is the length of gain medium, eta l is the ri, refractive index of gain medium, and eta c is equal to ri of the space. So it depends, if the space is air then it will be 1, and if it is not then it will have some other value. Now the mode number is noted as n, and that will be calculated 2 eta d nu by c, or 2 eta d by lambda. Now I'll just show an example, that is determine the mode number at the extreme ends of the optical frequency region for the following example. The wavelength lambda equal to 700 nanometer in the red, and a spacing of t equal to 0.35 meter. This is the first case, and another case is lambda equal to 400 nanometer in the blue region and a spacing of d equal to 0.4 meter. So here there is no mention of refractive index, so this is missing, so we'll just assume eta equal to 1. Then we will calculate for 700 nanometer n equal to 2 eta. Okay, so eta d by lambda equal to 2 into 1 into 0.35 by 700 into 10 to the power minus 9, which gives 1,000,000. So this is basically 10 lakh mode inside the cavity, and for 400 nanometer this is 2 eta d by lambda equal to 2 into 1 into 0.4 by 400 into 10 to the minus 9. This will be 2,000,000. So there are 20 lakh mode inside the longitudinal mode inside the cavity. So this type of question can be asked in the assignment and in the exam, because these are very short numerical type question where you have just need to calculate the mode or calculate the number of mode, or it is possible that you have to calculate the f or q of the cavity. Now again there is another type of yeah, so I got disconnected somewhere in during this discussion of this problem, I think. So this is a problem regarding the determine the mode number for two wavelength. One is 700 nanometer, and the space is d equal to 0.35 meter, and another is lambda equal to 400 nanometer and the space is 0.4. So using this formula n equal to 2 eta d by lambda, we get the mode number is 10 lakh here, and for 400 nanometer we get the mode number is 20 lakh. Now there is another way of calculating the mode number, which is very different from this one, and that is, here the statement of the problem is very big, so I will not write the whole problem, but I will just read it out. So this is example 4. So here the problem is a 0.1 meter long ND-arc laser rod is coated with a 99% reflector on one end and a 95% reflector on the other end. So this is a rod, then there is this mirror, 99%, 95%, and this has a length 0.1 meter. So determine the longitudinal mode spacing. How many modes could be operating if the gain bandwidth is a Lorentzian shape with a FWHM of 0.45 nanometer? So okay, so I will just write it down because otherwise people will be confused. So determine the longitudinal mode spacing. How many modes could be operating if the gain bandwidth FWHM of 0.45 nanometer and peak at 1.06 micrometer. So this laser is mode locked, so you don't need to know about the mode lock. Just understand that in a mode lock laser all the modes are lasing, so from all the modes you are getting the emission. Assume and assume that the maximum small signal gain is 10% at peak. Small signal gain is 10% at peak, and cavity losses, which is the extra losses, I mean they are here 5% loss from transmission, here 1% loss from transmission. So now there are 2% loss per pass. So after every pass there is a 2% loss, and the refractive index of Nd:YAG is 1.82. Okay, so the important values are given. I will just write down. The D is 0.1 meter, R1 is 0.99, R2 is 0.95, eta is 1.82. So delta nu equal to C by 2 eta D. So this is the spacing of modes. So C by 2 eta D is 3 into 10 to the power 8 by 2 into the differential index, that is 1.82. Then D is 0.1. So this will be 3 into 10 to the power 8.24 into 10 to the power 8 hertz. Now cavity loss is excluding mirror transmission equal to 2% per pass. So total round trip loss. So total round trip loss means that it is uh, reflecting from two mirrors, and then it is also suffering the losses from the passes. So it will be from first reflection it will be 0.1 minus 0.99, then there will be two pass for the one round trip, so that will also calculate the losses. So 0.02 plus 0.02, and then there is another loss from reflection, that is 1 minus 0.95. So this is 0.01 plus 0.02 plus 0.02 plus 0.05 equal to 10%. So now, or we can, so for one round tip there are two pass, so 10% per two pass, so we can say that 5% per pass average loss. So the here so average loss in the cavity is 5% per pass. Now the gain only exceeds the losses over a bandwidth equivalent to the FWHM of the emission line. So here the emission line width is delta nu equal to C by lambda square delta lambda. So here FWHM is 0.4 nanometer and it is 1.6 micrometers. So delta lambda uh, 3 into 10 to the power 8 into 0.45 nanometers, so 0.45 into 10 to the power minus 9 by 1.06 into 10 to the power minus 6 whole square, which will be 1.20 into 10 to the power 11 hertz. So this is the maximum emission width of the laser. So now, and the mode spacing is given by this quantity. So if all the modes are lasing, then that means that this is the emission line width. Suppose, I mean, this is a very line width. So now the modes will be like this. Okay. So this is the mode spacing. So here this thing is given by 1.220 into 10 to the power 11 hertz, and this thing is given by 8.24 into 10 to the power 8 hertz. So In that case, the number max number of longitudinal modes is 1.20 at the 1.20 into 10 to the power 11 by 8.24 into 10 to the power 8. So this will give, so here we will add just 1, because if you calculate this then you will get something like a fraction or something. So that's why after multiplying we will just add 1 and we will get something around 146 modes, because it is considered that it will be the number of modes should be a integer. So that's why we will just add 1. So, and it is also possible that there is one more, the last mode is not included in the emission line weight, but in the calculation it came, so we will have 146 modes. So this value will be something 145.6. That's why we will round it off and say that there is 146 modes are possible or participating in the lasing action. So again we will do the same type of problem. So it was exam 4, so this is ex5. So here again I am reading the statement of the problem, that is a helium cadmium laser is operating at 441.6 nanometer with a natural mixture of cadmium. Assume the laser has a gain of 6% per pass. For the isotope at its maximum emission frequency, the laser mirrors are separated by a distance of 0.4 meter and the mirrors have reflectivities of 96% and 99.9% at the laser wavelength. Assume that there are scattering losses of 1% per pass through the cavity. Also remember that the index of diffraction within a gas laser is 1. How many longitudinal modes would be lasing in this system? Okay, so the space so the mirrors are separated by 0.4 meter. R1 is 0.96, R2 is 0.999, lambda is 0.4416 nanometer. So scattering loss 1% per pass, that means 0.01 per pass. So round trip loss is 1 minus 0.96 plus 1 minus, so this is from the first mirror, this is for the second mirror. Now 0.0 0.01 plus 0.01. So this is almost 0.061 or 6.1%. So now another thing that is provided in the problem is that the bandwidth of the helium cadmium laser L is 2.56 gigahertz. And the mode spacing is C by 2D equal to 3 into 10 to the power 8 by 2 into 0.4, that is 3.75 into 10 to the power 8 hertz. So the modes is number of modes is equal to 2.56 gigahertz by 3.75 into 10 to the power 8 hertz plus 1, that will give 7.83, that is 8 modes. So in helium cadmium laser there are 8 modes that is actually participating in the lasing action. Now the value I have used for this delta nu L is 2.56 gigahertz, which is from the information that cadmium has 3 isotopes, CD112, CD110 and CD1160. Okay, so this one has a gain 10%, this one has a gain 5.2%, this one has a gain 3.2%. So considering the gain, that the loss is 6% here, so these two isotope will not do anything for this lasing action, so only this one will do the lasing. And then for this cadmium we have the bandwidth is 2.56 gigahertz. So this is the information that is not provided in the problem, but it will be provided in the uh, problem definitely. Here it is not provided in the problem, which I have to collect from somewhere. Then from that you have to use this and calculate the number of modes. So with this problem I will end the discussion on the longitudinal mode. But at the starting of the class I have mentioned about where is it so this is done. So there is this mode, transverse mode. So transverse mode is basically there are two kinds of mode, longitudinal and transverse. So if you want to understand that in case of laser, then I will say I will just draw the axis first. um, Set x, I think it's so now if I talk about the longitudinal mode, then this mode will be uh, in this direction, in the z direction, but transverse mode will be span over the xy plane. So if you have read about laser a little bit, then you might have heard about the term TEM00 mode. So this is the transverse mode. This looks like this. This is the transverse mode. So basically this span, so this is like this. So this is the transverse mode, but the calculation of this transverse mode is complicated, so I'll just write down the formula for this transverse mode, which is also not very easy, but anyway I'll just write it. UPQ XY equal to HP root over 2 square root of 2x by W sorry, UPQ xy equal to HP root 2x W HQ root 2y W e to the power minus x square plus y square by W square. So this is the form of the transverse mode of a laser beam which has a Gaussian profile. So particularly this part you can see this is a Gaussian which has a form of e to the power minus x square, but it is a two-dimensional Gaussian, so that's why it has a form of e to the power x square plus y square. Okay, and also here the x and y are symmetric, that's why this w is only one kind of w is there, this one. So this w is known as the beam waist, and this hp and hq are Hermite polynomial. So I'll just write down some value of this polynomial. So h naught of u is 1, h1 of u is 2u, h2 of u is 2 square minus 1, h3 of u is, oh sorry, I don't need to write the value of h3. I will just write that hm of u is minus 1 to the power m eu square dm e minus u square du. I don't think this transverse mode is necessary for any to solve the assignment or solve any problem in the exam, but it is a necessary concept to know about. So this is the tm. So this epq is the distribution for tem pq mode. Okay, so now I will just write down one example, that is, write out the mode distribution at mirrors for the TEM 00 and TEM 01 and also TEM 11. So here in terms of x, y and rho, where rho is root over x square plus y square. Okay, so I will just start with TEM 00 u00xy. So if you use this formula, this big formula, then p equal to 0, q equal to 0. So h0 this, h0 this, then this one. So h0 of u is 1. So this will be very straightforward. This part will be 1, this part will be 1, and then only this part. So I'll write from the beginning to, sorry, root 2x by w h naught root 2y by w e to the power minus x square plus y square by w square. So these two things will go to 1, then we will only have e to the power rho square minus w square. This is exactly the Gaussian we know. Now TM 01, so 01, so u 01 xy equal to h0 root over 2x w h1 root over 2yw e to the power x square y square w square. So now H0 u is 1 and H1u is 2u. So from here we will have a 1, from here we will have a 2u thing, so it will be uh, so the u will be replaced by root 2 y w by w, so it will be 2 root 2 y by w e to the power minus rho square w square. So as you can see, this is not a exact Gaussian or some like thing, rather than it has a y dependence here, so it will be not symmetric. Then again there is this TM11 mode, that will be u11 xy h1 root over 2x, so sorry, root over 2w h1 root over 2yw with power minus x square plus y square w square, so it will be 2u 2u, so root 2x w root 2y w e to the power minus rho square w square, 2xy w square w square w square. Oh, sorry, here it will be 2 2, so it will be 8 8xy by w square e to the minus rho square w square. So in this way you can find out the different TEM mode. So now I'll just show the plot of TEM 00, that so this is E. Again, if I convert it into the intensity, then it will have the same Gaussian type of form. My drawing is not symmetric by the way, but it should be. So this is one dimensional projection or one dimensional plot of the modes. But when we go to TM01, so this is basically from the point x equal to 0. So basically here is the beam, and this is x, this is y, and we are looking at x equal to 0. So x equal to 0 means we are looking at there, it is the point. So we are looking at this central line, and we have this Gaussian form. Now for TM01, if we look at it, we will see that there is a y dependence. So if there y is negative, then it will be negative, so like this. So E y, okay. Now this is I. So when we convert from electric field amplitude to intensity, it will be like this, then again this. So there will be two peaks, and two peaks are not exactly Gaussian, though I have drawn it as Gaussian, but it will be something like this, which is not Gaussian. So you will see this kind of two beams in the plane. So again we can write different mode like TM. I have already write the TM11. Now TM20, that will be U20XY. It will be H2 root over 2x W H naught 2y W e to the power minus x square plus y square W square. So this will be 2 2 root 2x W whole square minus 1, then 1, then e to the power minus x square y square W square. So 2 4 x square minus W square minus 1 minus rho square W square. Again similarly the TM22 will be U22XY H2 root over 2x W H2 root over 2y W is to the power x square plus y square W square. So this will be 8 x square W square minus 2 8 y square W square minus 2 e to the power minus x square plus y square W square. So you might think that why I am writing all these expression, but from a laser we can obtain this kind of modes. So it's not necessary that whatever you see in any image or any from any laser that is this, because people mostly use this TEM00 mode, but that should not mean that the laser only had this mode. Laser also had this kind of mode. It is very possible to obtain this different kind of mode, but mostly people use this TEM00. That's why it has a beautiful Gaussian shape. So for a laser beam, if you look at here, you will see this. So this is y, this is x. So you will have a two-dimensional Gaussian shape in the laser, and if you project it on one of a axis, you will have a one-dimensional Gaussian along both the axes. Now if we talk about the TEM00 mode, which is mostly used, the electric field will be E naught e to the power rho square W square. So then I will be I naught e to the power 2 rho square W square. So then, so what is the property of this W? So let's just put rho equal to W. Then we'll have I equal to I naught e to the power or I naught square. And if we calculate the E, then it will be E naught by E. So basically at rho equal to W, the electric field is reduced to its 1 by E amplitude. Also from here you can find out the e to the power 2 square. You can find out the, so this is one kind of beam diameter, that is the 1 by e or 1 by e square diameter. This is also, you can find out the FWHM. So by FWHM we will write I equal to I naught by 2. So I naught by 2 equal to I naught. So this will be e to the power 2 half equal to e to the minus 2 rho square w square. So it will be 2 rho square w square equal to ln 2. That will be rho. Okay, so there are two kind of diameter you can think of beam, that is this. So 1 by e square is somewhere here, 1 by e square diameter, and then there is this is FWH. So when we talk about the beam spot size, we can either write the FWHM, which is this one, or this thing, 1 by e square diameter. So these two things are used to denote a Gaussian beam, or to denote the spot size of the beam. So the spot size is used when we focus the beam, or we use something like a laser has a particular spot size, and then it is focused through the our desired size or the beam spot. But the spot size is very necessary, because when you are focusing a beam, so basically when we have a bigger spot size, the Gaussian beam will have a distribution like this. Okay, but when you reduce focus this, then it will have a same power. The power will be lost through, because it is going through a lens or an optical element, so there will be certain loss due to scattering, absorption, reflection, and all those things. But the whole Gaussian will be compressed to a small spot, and then you will have a different type of distribution. So that means that the whole this part is compressed here. So this will mean that the beam is compressed in space, and that's why the central part will have a very bright spot. That means the central spot has a very high intensity. So this kind of focused beam is very dangerous, and it can actually burn. So whenever there is a focusing is there, we need to be careful in the laboratory, because the peak power is very high at that particular point. Because a lens can focus for example, or from my experience I can say 3 mm to 100 micrometer. This is I am talking about 1 by square diameter. Any doubt?
No, sir. Thank you.
Okay, so if there is no doubt, then I will end today's class and I will meet on next Friday again. So I am ending today's session. Thanks for joining everyone.